Alpha Centauri is close enough that if you fired a beam of light toward it tonight, the signal would arrive in just over 4 years, and a reply would take less than 9 years to return. That sounds immediate until you try to reach it. The nearest star system is not one star, but three, bound together in a slow gravitational dance that began before Earth had oceans, before its surface cooled, before life had any chance to exist. One of those stars holds a planet roughly the size of Earth, orbiting at a distance where liquid water could exist. We found that planet in 2016. We still do not know what is on its surface. The fastest spacecraft humanity has ever built would take tens of thousands of years to make the journey, and yet there is a real project operating right now designed to reach that same destination in just 20 years using nothing but light. The distances involved are so large they begin to distort what time actually means. The signal you send today arrives years later. The image you see tonight left before you made the decision to look at it. What looks like a neighboring star is not nearby in any human sense. It is separated by a stretch of space so vast that crossing it would change everything about the body, the mind, and the experience of time itself. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Let's begin with what that distance actually is. If you trace the southern sky on a clear night, your eyes eventually settle on a bright, steady point low on the horizon. That point is Alpha Centauri, anchored within the constellation Centaurus, a region known for centuries to those who lived beneath southern skies. For navigators across Africa, Polynesia, and Australia, this was not abstract astronomy. It was direction. It was survival. Among Aboriginal Australians, these stars formed part of what is often called the two pointers, guiding the eye toward the Southern Cross. This use stretches back thousands of years, long before telescopes, long before written records. The sky was already mapped in memory. But what we are looking at is not a single star. It only appears that way. The name itself comes from the system introduced by Johann Bayer in the year 1603. In that system, Alpha marks the brightest star in a constellation. Yet here, brightness hides complexity. Alpha Centauri is three stars, bound together by gravity across immense distances. The first is Alpha Centauri A. It is a G-type star, meaning it burns hydrogen much like our Sun. Its mass is about 1.1 times that of the Sun, and its luminosity, the total energy it emits, is roughly 1.519 times greater. Its surface temperature rests near 5,790 Kelvin, giving it a familiar golden white glow. Close beside it moves Alpha Centauri B. Slightly smaller, cooler, and deeper in color, it is a K-type star. Its mass is about 0.9 times the Sun's, and its surface temperature is around 5,260 Kelvin. The light it gives off leans toward orange. These two stars orbit each other in an elongated path. At their closest, they are separated by about 11 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. At their farthest, that distance stretches to 36. This slow gravitational dance takes decades to complete. But there is a third member, quieter and more distant. Proxima Centauri is a red dwarf, small and faint, with only about 0.12 times the Sun's mass. It emits so little light that it cannot be seen with the naked eye, even though it is the closest individual star to Earth at roughly 4.243 light-years away. A light-year, simply put, is the distance light travels in 1 year. Proxima does not circle tightly with the other two. It drifts far beyond them at a distance of about 13,000 astronomical units. One full orbit takes around 550,000 years. A motion so slow it feels almost still. But the entire system is not fixed in place. It is moving. Over the next 28,000 years, Alpha Centauri will draw closer to our solar system, reaching a minimum distance of about 3.26 light years before gradually receding again. A slow approach, then a quiet departure. For most of human history, distance in the sky did not exist. Every star seemed pinned to the same surface, equally far, equally unreachable. You could see brightness, color, motion across seasons, but not depth. The universe above you was a flat map, but a subtle shift began to change that. As Earth moves around the sun, our viewpoint changes across the year. Nearby stars appear to shift slightly against the more distant background. This effect is called stellar parallax, a tiny apparent motion caused purely by perspective. It is almost imperceptible, yet it carries distance within it. In the early 19th century, this idea moved from theory to measurement. In the year 1832, Thomas Henderson, working at the Cape of Good Hope in South Africa, carefully recorded the position of Alpha Centauri over time. His goal was simple in concept, difficult in execution: detect the shift, measure the angle, translate it into distance. But Henderson hesitated. The shift he observed was so small that he questioned his own data. The angle measured less than a single arcsecond, which is 1/3600th of a degree. Such precision was at the limits of his instruments. So he waited. He checked again. He delayed publication. By the time he released his results in 1839, another astronomer had moved faster. Friedrich Bessel had already published a successful parallax measurement for the star 61 Cygni in 1838. That result became the first widely accepted measurement of stellar distance. Henderson's work, though accurate, arrived second, but it still mattered. His calculations showed that Alpha Centauri lay about 4.3 light years away. For the first time, we understood that this system was not just bright, it was close, closer than anything else known. That realization changed how we looked outward. But the story did not end there. Decades passed, instruments improved, and the sky revealed more detail. In 1915, Robert Innes, working in Johannesburg, noticed something unusual. A faint red star moved across the sky with the same proper motion as Alpha Centauri A and B. Proper motion means the actual movement of a star through space relative to more distant stars. This was not coincidence. The faint object was gravitationally linked, part of the same system. It was later named Proxima Centauri, from a Latin word meaning nearest. Its measured distance turned out to be slightly less than the other two stars. Not by much, but enough to claim a title that still holds: the closest known star to Earth. Modern instruments refined these measurements further. Space-based observatories removed the distortion of Earth's atmosphere, allowing unprecedented precision. The Hipparcos mission, launched in 1989, mapped stellar positions with remarkable accuracy. Later, the Gaia mission improved that precision even more. Today, the distance to Alpha Centauri is measured at approximately 4.2465 light years. The uncertainty is now a fraction of a percent. A shift smaller than the width of a human hair, measured across space, revealed our nearest neighbor. If you could watch this system over centuries, you would notice a slow, deliberate motion. 2 points of light circling one another, not in a perfect circle, but along a stretched path that repeats with quiet precision. This is not a brief interaction. It has been unfolding for about 4.85 billion years. You are watching a binary system. A binary star system is simply two stars bound by gravity, orbiting a shared center of mass, which is the balance point between them. Neither star sits still. Both move, constantly adjusting to the pull of the other. Alpha Centauri A and B complete one full orbit in about 79.91 Earth years. For us, that is a lifetime. For them, it is a single cycle in a long sequence that is repeated since before Earth settled into its present form. Their path is not uniform. At their closest approach, called periastron, the stars are separated by roughly 11 astronomical units. At their farthest, that distance expands to around 36. This shifting separation means their gravitational influence is constantly changing in strength. The last periastron occurred in the year 1955. The next will arrive around 2035. A slow rhythm measured across generations. From Earth, the pair often appears as a single bright point. But with a modest telescope, even one used by amateur observers, the light resolves into two distinct stars. The separation becomes visible, the motion becomes real. But gravity does more than guide their orbit. It shapes everything around them. Any planet attempting to orbit either star must exist within a stable zone where the gravitational pull of the companion does not disrupt its path. Computer simulations suggest that planets can maintain stable orbits up to about 3 astronomical units from either star. Beyond that, the shifting pull of the binary companion introduces instability over long timescales. This constraint narrows the regions where planets might survive. Alpha Centauri b draws particular interest here. Its lower luminosity, meaning it emits less energy than its companion, places its habitable zone closer to the star. The habitable zone is the region where temperatures could allow liquid water on a planet's surface. Closer orbits make detection easier. Astronomers often rely on the radial velocity method, which measures the slight wobble of a star caused by an orbiting planet's gravity. Smaller orbits produce stronger signals. This makes Alpha Centauri b an appealing target. In the year 2012, a European research team announced the detection of a planet around this star. The signal suggested a small Earth-sized world, later named Alpha Centauri b. The announcement carried weight. It hinted that even our nearest stellar neighbors might host planets, but the signal did not hold. By 2015, further analysis revealed that the detected pattern was likely an artifact, a false signal produced by subtle noise within the data itself. The planet was not confirmed. The excitement faded into caution. This moment reshaped expectations. It showed how difficult it is to detect planets, even in systems so close to us. Precision must reach extraordinary levels, and even then, certainty remains fragile. So far, no confirmed planets orbit Alpha Centauri A or B. But the search continues, growing more sensitive with each new instrument, each new method, each patient return to the same quiet orbiting light. On a late August day in the year 2016, a quiet announcement carried enormous weight. A team led by Guillaume Anglada Esquide, working with observations gathered over years, confirmed the presence of a planet around Proxima Centauri. The findings appeared in the journal Nature. It was not a distant abstraction, it was a world at our doorstep. We did not see the planet directly. Instead, its presence was revealed through motion. The method is called radial velocity, which means measuring the slight back and forth movement of a star along our line of sight. As a planet orbits, its gravity pulls the star into a small wobble. That wobble shifts the star's light very slightly, toward red as it moves away, toward blue as it moves closer. From that shifting light, the planet emerged. This world, now known as Proxima b, completes an orbit in just 11.2 Earth days. That is its year. It circles extremely close to its star, far closer than Mercury sits to the Sun. By familiar standards, it should be scorched. But the star it orbits is faint because Proxima Centauri emits so little energy, the region where liquid water could exist, the habitable zone, lies very near to the star. Proxima b sits within that narrow band. It receives about 65% of the energy Earth receives from the Sun. Less warmth, but not necessarily too little. Its mass adds another piece to the picture. At minimum, Proxima b holds about 1.17 times the mass of Earth. The true value could be higher, depending on the tilt of its orbit, which we cannot yet measure. This places it firmly in the category of terrestrial planets, meaning rocky worlds rather than gas giants. Its surface gravity is likely similar to ours, perhaps slightly stronger. You could stand there in principle, but everything depends on something we have not yet seen: an atmosphere. Without an atmosphere, the planet would be exposed to the full contrast of its position. The side facing the star would heat continuously, while the far side would remain in permanent darkness. Temperatures would swing between extremes, leaving little room for stability. But with a sufficiently thick atmosphere, heat could be transported across the surface. Winds could carry energy from day to night, softening the contrast. In that case, regions of the planet might allow liquid water to persist. A fragile balance, but possible. This uncertainty defines the world. In the year 2020, astronomers reported evidence of another object in the system called Proxima Centauri. It appears to be a larger planet, a super-Earth, orbiting much farther from the star, with a period of about 5 years. Its existence remains uncertain, its signal still debated. So we return to Proxima b, a planet close enough to measure, yet still hidden in essential ways, a surface we cannot see, an atmosphere we cannot confirm, a place balanced between what we know and what we can only infer. The star at the center of this world does not behave quietly. Proxima Centauri belongs to a class known as flare stars, meaning it releases sudden bursts of energy that can outshine its normal output many times over. These eruptions are not rare. They are part of its nature. A flare is a rapid release of magnetic energy from the star's surface, sending radiation outward across space. That radiation includes ultraviolet and X-rays, forms of light far more energetic than what we see. They carry enough energy to break molecular bonds. In March of the year 2016, astronomers recorded a particularly intense event. For a short time, Proxima became about 1,000 times brighter in ultraviolet light than usual. The flare passed quickly, but its effect would not be brief for anything exposed to it. Such events accumulate. Over long stretches of time, repeated flares would erode a planet's atmosphere. High-energy radiation can strip away gases, especially lighter ones, gradually thinning the protective layer that surrounds a planet. Without that layer, the surface becomes exposed. A study published in the year 2017 estimated that Proxima b receives roughly 250 times more X-ray radiation than Earth receives from the Sun. That is not a small difference. It is a constant pressure acting against any atmosphere the planet might try to hold. But survival is not impossible. For life to persist under such conditions, certain protections would need to exist. One possibility is a strong magnetic field, a global shield generated by the movement of liquid metal within the planet's core. This field could deflect charged particles, reducing atmospheric loss. Another option is a very thick atmosphere. If dense enough, it could absorb incoming radiation before it reaches the surface. Even as some gas escapes over time, enough might remain to maintain stability. There is also a third path. Life could exist beneath the surface. Underground environments or deep oceans would provide natural shielding, blocking most harmful radiation. In such places, energy might come from chemical reactions rather than sunlight. This would create a very different kind of biosphere. But radiation is only part of the challenge. Proxima b is likely tidally locked. This means one side of the planet always faces the star, while the other remains in permanent darkness. The same pattern we see with the moon, but on a planetary scale. This creates a stark division. The day side receives constant energy. The night side receives none. Without an atmosphere, temperatures would diverge dramatically, one hemisphere heated, the other frozen. But models of atmospheric circulation suggest a more complex picture. If a substantial atmosphere exists, winds could transport heat from the day side to the night side. This redistribution could moderate extremes. In that case, a narrow region might emerge between light and dark. This boundary is called the terminator, the line dividing day from night. Along this shifting edge, temperatures could settle into a stable range, neither too hot nor too cold. A band of potential habitability wrapped around the planet. It is a fragile possibility, yet it remains one of the most studied ideas in modern astrobiology, a reminder that even under constant radiation, even in a locked orbit, conditions may still find a way to balance. Imagine lifting your gaze from a surface that never sees a blue sky. Above you, the star does not rise or set. It hangs fixed, steady, unblinking, as if the passage of time has lost one of its oldest markers. You are on a world where the sky does not move in familiar ways. Proxima Centauri dominates that view. From this distance, it appears roughly 3 times wider than our sun looks from Earth. Not brighter in the way you might expect, but larger, closer, more present. Its light carries a deep orange-red tone, shifting everything beneath it into unfamiliar color. Shadows stretch differently. Surfaces absorb a warmer glow. The landscape would never look neutral. Every object, every texture would exist under this constant reddish illumination. The idea of a white surface, of a blue horizon, would not exist here. Even the concept of daylight feels altered, stretched into something continuous. But the star does not remain stable. At unpredictable moments, Proxima releases flares. During these events, it briefly floods the surroundings with high-energy radiation. Much of this light would be invisible to human eyes, but its effects would be immediate. The surface would be bathed in energy that interacts directly with matter. These bursts would pass quickly, but they would leave their mark, shaping the environment in ways not immediately visible. The sky, for those moments, would hold more than color. It would carry intensity. If you move toward the boundary between light and darkness, the experience would shift again. At the terminator, where the permanent day side meets the endless night, the star would sit low on the horizon, frozen in place. Its light would skim across the surface, creating a constant twilight. The sky here might allow a transition, a region where both sides of the planet can be sensed at once. Step further into darkness. On the night side, the sky opens. Without the star overhead, other lights emerge. 2 bright points stand out immediately, Alpha Centauri A and B, distant but striking. They would appear separated by about 2 degrees, roughly 4 times the width of the full moon as seen from Earth. They would not twinkle softly. They would shine with a steady brilliance among the brightest objects in that sky. Their light would feel precise, almost sharp against the darkness. And then, among countless others, one familiar star appears. Our Sunday. From this distance, it becomes just another point of light, bright but not dominant, sitting within the pattern of Cassiopeia. It would not draw attention unless you knew what it was, a small star among many. The perspective shifts quietly. Everything we consider central becomes peripheral. Everything that defines our sky becomes distant. Yet one thing remains unchanged. The Milky Way stretches across the sky in the same broad arc, its structure nearly identical. We have not moved far enough to alter the galaxy, only enough to change what feels important. Numbers alone do not carry distance well. You can hear them, repeat them, even memorize them, and still feel nothing. But here, we have to slow down and let one number unfold. A light year. It sounds like time, but it is distance. It is how far light travels in 1 year, moving at about 300,000 kilometers each second. Over that span, light covers roughly 9.461 trillion kilometers. That is 1 unit. Now place 4.37 of those units end to end. That is the separation between us and Alpha Centauri, about 41.3 trillion kilometers of space, empty and silent, stretching without markers or edges. Nothing in our daily experience prepares us for this scale, so we reach for comparisons. If you set out in a car moving at 100 kilometers per hour, never stopping, never slowing, the journey would take about 47 million years. Not a lifetime, not a civilization. Entire branches of evolution would begin and end while you traveled. But cars are not built for space, so we look at our fastest machines. Voyager 1, the most distant human-made object, is moving at about 17 kilometers per second. At that speed, it would take roughly 73,000 years to reach Alpha Centauri, assuming it were pointed in the right direction. It is not. Even the fastest humans have ever moved does not change much. The crew of Apollo 10 reached about 11 kilometers per second during re-entry. At that velocity, the journey would still require around 115,000 years. These speeds feel extraordinary to us, but they are insignificant here. Light itself makes the trip in 4.37 years. That is the upper limit of speed in our universe, the fastest anything can travel. Everything else falls far behind. The gap between our technology and that limit defines the problem. But the difficulty is not only physical, it is also conceptual. When we say that the nearest star is over 4 light-years away, we are describing a distance so large that all of recorded human history fits inside it many times over. Every language, every city, every moment you know exists within a fraction of that span. This is what astronomers confront. Not just large numbers, but a boundary that reshapes expectation. The idea that even the closest destination beyond our system lies so far beyond immediate reach changes how we think about exploration. You begin to see why proximity in space does not mean accessibility. It only means less impossible. And even that difference is vast. In the year 2016, while one discovery was still settling into place, another idea appeared with quiet urgency. It did not describe a distant future. It described a method, outlined in present terms, funded and studied in real time. The initiative was called Breakthrough Starshot, announced by Yuri Milner as a research effort valued at $100 million. The goal was simple to state, difficult to accept: reach Alpha Centauri within a human lifetime. But the approach abandoned familiar spacecraft entirely. Instead of one large vehicle, the plan proposed thousands of extremely small probes. Each one, called a star chip, would be no larger than a postage stamp and weigh only a few grams. not a ship you could imagine boarding. Each chip would carry a sail. This sail would be an ultra-thin reflective surface, stretching several meters across while remaining only a few hundred atoms thick. Its purpose would not be to catch wind, but light itself. Photons, the particles of light, carry momentum. When they strike a reflective surface, they exert pressure. That pressure becomes thrust. A ground-based laser array, potentially covering about 1 square kilometer, would focus intense beams onto these sails. The array would generate around 100 gigawatts of power, directing it with extreme precision. As the light strikes the sail, it would push continuously, accelerating the tiny craft. Within minutes, the star chip would reach extraordinary speed, about 20% of the speed of light, which is roughly 60,000 kilometers per second. At that velocity, the journey to Alpha Centauri would take around 20 years. Data sent back would require another 4.37 years to arrive, a round exchange measured in decades. But the concept rests on challenges that are not easily solved. The sail must endure the laser burst without melting or tearing under extreme stress. It must remain stable while being accelerated to relativistic speed, which means a significant fraction of light speed. And then comes the journey itself. Interstellar space is not empty. It contains sparse particles and microscopic dust grains. At 60,000 kilometers per second, even a tiny particle becomes a high-energy collision. A grain smaller than a millimeter could damage or destroy a craft of this scale. Navigation adds another layer. Each star chip must remain oriented correctly, maintain communication, and operate instruments, all within a mass measured in grams. Every component must be reduced, simplified, yet still capable of meaningful observation. Despite these obstacles, the physics behind the idea remains sound. The project gained public support from Stephen Hawking, who described it as the next great step in exploration before his death in 2018. His involvement reflected the seriousness of the proposal. As of the mid-2020s, Breakthrough Starshot remains in development. No launch date has been set. No craft has yet been sent. But the concept continues to be refined, tested, and debated. It stands as a shift in thinking, where reaching another star is no longer only theoretical, but something being actively engineered. Between stars, there is no clear emptiness. What seems like a void is filled with a faint presence, a mixture known as the interstellar medium. This medium consists of gas, dust, and charged particles spread thinly across enormous distances. You would not notice it at rest. But motion changes everything. At the speeds imagined for interstellar travel, even the smallest particle becomes significant. A spacecraft moving at 20% of the speed of light encounters this medium, not as background, but as impact. Each collision carries energy far beyond everyday experience. A single hydrogen atom becomes a projectile. Hydrogen is the simplest element, just one proton and one electron. Yet at 60,000 kilometers per second, its collision releases energy comparable to high-energy radiation striking a surface. Multiply that by countless encounters over years, and the effect becomes cumulative. Dust presents an even greater concern. A particle measuring just 1/10 of a millimeter across, almost invisible by ordinary standards, would strike with the force of a small explosion at these velocities. The kinetic energy, meaning the energy carried by motion, increases with speed. At relativistic speeds, where motion approaches the speed of light, that energy becomes extreme. The density of this dust is low. Estimates suggest roughly 1 grain per cubic kilometer between us and Alpha Centauri. That sounds negligible. But over a journey spanning more than 4 light years, the number of potential impacts grows. Each grain represents a risk, so the challenge becomes one of survival. Engineers have proposed several solutions. One approach involves placing a thin, protective shield at the front of the craft, made from materials such as beryllium, copper, or graphite. These materials combine strength with low weight, absorbing or deflecting incoming particles. Another idea focuses on design. If the spacecraft presents a smaller cross-sectional area, meaning a smaller surface facing forward, it reduces the probability of impact. Orientation becomes a form of protection. Some proposals even consider sails capable of self-repair, structures that could recover from minor damage over time. This introduces new complexity, but also resilience. But beyond dust, there is a larger transition. As a spacecraft leaves our solar system, it passes through the heliosphere, a vast region shaped by the solar wind. The solar wind is a stream of charged particles flowing outward from the sun, creating a protective bubble that extends roughly 100 astronomical units. At its boundary lies the heliopause. This is where the influence of the sun gives way to the interstellar medium. In the year 2012, Voyager 1 crossed this boundary, becoming the first human-made object to enter interstellar space. Its instruments recorded changes in particle density and radiation, confirming many predictions while revealing unexpected variations. Beyond this point, cosmic radiation increases. These high-energy particles, originating from distant supernovae and other energetic events, pass through space with little obstruction. For small probes, this presents a hazard to electronics. For human missions, it presents a deeper problem. Shielding against such radiation requires mass, and mass requires energy to move. The more protection you add, the harder it becomes to reach the necessary speeds. This balance between safety and propulsion remains unresolved. So the path between stars is not empty. It is filled with obstacles too small to see, yet powerful enough to define the limits of travel. Long before light was considered a means of propulsion, another idea took shape, one that relied not on subtle pressure, but on controlled force. In the late 1950s, a group of physicists began outlining a method that did not avoid explosions, but embraced them. The concept became known as Project Orion. It was developed by researchers, including Freeman Dyson and Ted Taylor, working through General Atomics. Their proposal was direct: use nuclear detonations to push a spacecraft forward. The mechanism was mechanical. A large plate would be positioned at the rear of the ship, designed to absorb repeated impacts. Behind it, nuclear devices would be released and detonated in sequence. Each explosion would generate a burst of high-pressure plasma, striking the plate and transferring momentum. That momentum would be dampened by a system of shock absorbers, then carried through the structure. Pulse by pulse, each detonation would push the craft forward, building speed gradually over time. Unlike chemical rockets, which rely on continuous combustion, this system would deliver thrust in discrete intervals. The energy released by each pulse far exceeded that of conventional fuel. Calculations suggested remarkable outcomes. An Orion-class vessel could reach speeds between 3 and 10% of the speed of light. That range, while modest compared to more recent concepts, represented a dramatic leap beyond any propulsion system then imagined. At 3% of light speed, a journey to Alpha Centauri would take roughly 145 years. Not quick, but within reach of a multi-generational mission. Such a mission would involve crews living and dying aboard the vessel, with descendants continuing the journey. The concept moved beyond engineering into sociology, but the physics remained consistent. But the project did not continue. In the year 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear detonations in space. The legal and political landscape shifted, and Project Orion was abandoned. The idea remained on paper, technically plausible, but no longer viable within existing constraints. Still, the concept evolved. In the 1970s, the British Interplanetary Society proposed a refinement called Project Daedalus. This design replaced nuclear fission with nuclear fusion, using isotopes such as deuterium and helium-3 as fuel. Fusion releases energy by combining atomic nuclei rather than splitting them, offering higher efficiency and fewer radioactive byproducts. The propulsion method changed, but the goal remained. Daedalus was designed as an unmanned probe capable of reaching about 12% of the speed of light. At that velocity, the journey to Alpha Centauri would take approximately 50 years. It would not slow down upon arrival. It would pass through, collecting data during a brief encounter. A flyby, not a landing. Neither Orion nor Daedalus was ever constructed. The challenges of engineering, cost, and political approval remained too great, but their significance lies elsewhere. They showed that interstellar travel does not violate the laws of physics. It demands scale, energy, and commitment far beyond current systems, but it remains within the realm of possibility, an idea that persists quietly, waiting for conditions to change. There is another way to cross a distance that refuses to shrink. Instead of shortening the journey, you extend the traveler. The ship becomes more than a vehicle. It becomes a world that continues while space slowly passes outside. This is the idea of a generation ship. A generation ship is a self-sustaining spacecraft where people live entire lives and their descendants continue the voyage. The destination is not reached by the original crew, but by those born along the way. Time is no longer an obstacle. It is part of the design. At a speed of about 0.5% of light, a journey to Alpha Centauri would take roughly 850 years. That is not a mission. It is a lineage. Over that span, perhaps 30 to 40 generations would be born, grow, and pass on within the vessel. You are not traveling, you are continuing. But this changes the nature of the problem. Engineering alone is no longer enough. The question becomes social. How do you sustain a community across centuries when most individuals will never see the destination they are meant to reach? Purpose must persist without direct experience. Those who arrive would have no memory of Earth. They would inherit knowledge through records, through education, through stories shaped by repetition. The origin becomes abstract, something known but never felt. But continuity requires more than culture. Population genetics introduces strict limits. A small group risks inbreeding, which reduces genetic diversity and increases the likelihood of inherited conditions. Studies suggest a minimum of about 98 individuals might sustain diversity under controlled conditions. But this number assumes careful management. In practice, more is needed. Some estimates place the minimum viable population in the hundreds. A study published in the year 2018 by Cameron Smith proposed that a population of around 10,000 would provide a stable balance, large enough to support variation, small enough to remain manageable. But numbers alone do not create stability. Every system required for life must function continuously. Food must be grown, not stored. Water must be recycled. Air must be maintained through closed ecological cycles, systems where outputs are reused as inputs, These systems must operate without interruption for centuries. And then there is governance. A society confined within a finite structure must develop rules, institutions, and methods of resolving conflict. Disagreements cannot be avoided by distance. They must be addressed within the same space, again and again, across generations. Psychological health becomes central. Isolation from any external world, combined with repetition of environment, creates pressures that we have only begun to study. Even short-term confinement on Earth produces measurable effects. Extending that across centuries introduces uncertainties we cannot fully model. But the concept remains consistent. No such ship has been built. No design has moved beyond theory. Yet the idea reveals something deeper than propulsion limits. It suggests that reaching another star may depend less on speed and more on whether a civilization can sustain itself, unchanged in purpose, across time that no individual can fully experience. Time feels steady when you sit still. Seconds pass with quiet regularity, one after another, forming a rhythm you rarely question. But motion changes that rhythm in ways that are not intuitive. In the year 1905, Albert Einstein described a framework called special relativity. Within it lies a prediction that challenges everyday experience. Time does not pass at the same rate for all observers. It depends on velocity. This effect is called time dilation. Time dilation means that a moving clock ticks more slowly compared to one at rest. The faster you move, the more pronounced the difference becomes. It is not a perception. It is a measurable change in the flow of time itself. We have tested this. Atomic clocks, which measure time using the vibration of atoms, have been flown on aircraft and compared to clocks on the ground. The clocks in motion fall slightly behind. Satellites used for global positioning must adjust for this effect continuously. Without correction, navigation would drift. At low speeds, the difference is small. If a spacecraft travels at about 10% of the speed of light, the time experienced aboard is only slightly less than time on Earth. The effect exists, but it remains subtle. Days feel like days. Years remain nearly aligned. But as speed increases, the divergence grows. At 50% of light speed, for every year experienced on the spacecraft, about 1.15 years pass on Earth. The difference is noticeable. Time is beginning to separate. At 90%, the effect becomes striking. 1 year aboard corresponds to roughly 2.3 years on Earth. The gap widens with each passing moment. Push further. At 99% of light speed, a single year for the travelers equals about 7 years for those who remain behind. At 99.9%, that ratio stretches to roughly 22 years for every year experienced aboard. The relationship is not linear. It accelerates. This creates a possibility that feels almost paradoxical. A crew traveling at near light speed could cross vast distances while experiencing only a small passage of time. For them, the journey might last a few years. For Earth, decades or centuries would unfold. The separation becomes more than distance. It becomes temporal. But not all missions reach such speeds. The small probes envisioned in current designs travel at about 20% of light speed. At that velocity, time dilation is present but modest. The clocks aboard run slightly slower, but not enough to reshape experience. For future crewed missions, the situation changes. As velocities approach relativistic levels, meaning a significant fraction of light speed, the difference in time becomes central to the journey. Communication delays grow. Return becomes complicated not just by distance, but by the passage of time on Earth. You would leave one moment and return to another, not because time moved differently for you in a subjective sense, but because motion altered its rate. The journey would carry you across space, yes, but also along a path where time itself unfolds unevenly, depending on how fast you choose to move. At first, nothing seems to change. You look outward, and the sky holds its familiar arrangement, stars fixed in patterns you could almost recognize, slowly shifting as the craft begins to move. Motion feels gentle at the start, but speed builds. As velocity increases, the geometry of what you see begins to distort. A subtle effect appears, known as aberration. Aberration means that light from different directions bends toward your direction of motion, not because space changes, but because you are moving through it. The stars ahead begin to crowd together. The sky tightens. Constellations stretch and lose their familiar shapes. Points of light that once seemed evenly spread now drift inward, gathering toward a central region directly in front of you. It is as if the universe is being pulled forward. At the same time, color begins to shift. Light has wavelength, which determines its color. When you move toward a source of light, those wavelengths compress, becoming shorter. This is called blue shift. Stars ahead begin to glow with a cooler, brighter hue, shifting toward blue and even beyond visible light. They intensify. Behind you, the opposite occurs. Wavelengths stretch, becoming longer. This is called redshift. Stars fade into deeper red tones, then into infrared, eventually slipping beyond what your eyes could detect. The sky behind darkens. Direction becomes everything. At high velocity, approaching 90% of the speed of light, the transformation becomes dramatic. Nearly all visible stars concentrate into a narrow cone ahead. The rest of the sky falls away into darkness. You are no longer surrounded by a sphere of stars. You are facing a tunnel of light. Within that cone, brightness increases. The combined effect of aberration and blue shift concentrates energy forward. Stars that were once faint now appear more luminous. The sky ahead becomes a dense field of sharpened points. And then, the destination itself begins to change. As you approach Alpha Centauri at these speeds, its light shifts as well. Radiation that was once visible arrives partly in ultraviolet. The star appears more intense, its spectrum altered by your motion. What you see is not only the star itself, but the effect of speed on its light. Nothing looks as it did before. But the transformation is not permanent. As the craft slows, the effects begin to reverse. Aberration relaxes. The stars spread outward again. Blue shift diminishes, colors returning toward their original wavelengths. The narrow cone widens. The sky unfolds. Gradually, the familiar distribution of stars reappears, though from a new vantage point. The distortion fades, replaced by a more balanced view. Motion gives way to stillness. No human has witnessed this directly. No camera has recorded such a journey. Everything described here comes from the equations of relativity, tested in laboratories and observed in smaller effects. These equations, precise and consistent, allow us to predict what sight would become at these speeds. We have not seen it, but we understand it well enough to know how the universe would change as you move through it at the edge of what is possible. Time leaves traces in stars, but not in ways we can see directly. You do not watch a star grow older. You infer it carefully from composition, motion, and the light it gives. From those measurements, a quiet conclusion emerges. Alpha Centauri A and B are old. Their estimated age is about 4.85 billion years. That places them slightly ahead of our own Sun, which formed around 4.6 billion years ago. The difference, about 250 million years, sounds small when compared to billions, but scale changes its meaning. On Earth, 250 million years is not a minor interval. At that point in our history, dinosaurs had not yet appeared. The supercontinent Pangaea was beginning to fracture, reshaping the surface into separate landmasses. Life on land existed, but it was simpler, dominated by early reptiles and primitive plants. Complexity was still unfolding. If we consider how long life on Earth took to develop from single-celled organisms into a technological civilization, the span approaches 4 billion years. That process was gradual, shaped by environmental stability, chance, and countless evolutionary steps. So what does an extra 250 million years represent? It is not a guarantee, but it is an extension of opportunity. If a planet around Alpha Centauri experienced conditions similar to early Earth, if it held liquid water, a stable atmosphere, and chemical ingredients for life, then biological processes could have begun earlier. Given more time, complexity might have advanced further. This idea is approached with caution. Astrobiologists do not assume that life arises easily or that it follows the same path everywhere. The emergence of life remains uncertain, perhaps rare, perhaps dependent on conditions we do not fully understand. Intelligence, even more so, may not be an inevitable outcome, but time matters. It provides a window during which processes can unfold. It allows for accumulation, for variation, for selection in a system older than ours. That window opened earlier. There is another factor to consider. The composition of these stars shows a slightly higher metallicity than our Sunday metallicity. In astronomy, refers to the abundance of elements heavier than hydrogen and helium. These elements form the building blocks of rocky planets. A higher metallicity increases the likelihood of planet formation. Observational studies have shown that stars with more heavy elements tend to host more rocky worlds. These are the environments where solid surfaces exist, where liquids can collect, where chemistry can persist over long periods. Gas giants dominate in some systems, but rocky planets offer different possibilities. So when we look toward Alpha Centauri, we are not only looking at proximity, we are looking at a system that formed earlier with a composition that favors the formation of terrestrial planets, a place where time and material conditions align in ways that invite careful attention, not certainty, but context. And in that context, the question of what might have developed there becomes harder to dismiss, not because we expect an answer, but because the conditions make the question worth asking. Far from Earth, beyond the interference of atmosphere and weather, a telescope unfolds in silence. Its mirrors align, its instruments cool, and it begins to collect light that has traveled for years. This is James Webb Space Telescope, launched on December 25, 2021. Its primary mirror spans 6.5 meters. That mirror gathers faint infrared light, which is heat radiation emitted by objects too cool or too distant to be seen clearly in visible wavelengths. Infrared allows us to detect subtle signals, including the warmth of planets that do not shine on their own. But Alpha Centauri presents a difficult target. The stars in that system are bright, overwhelmingly so compared to any planets that might orbit them. A planet reflects or emits only a tiny fraction of its star's light. When viewed from afar, that faint signal is lost, buried in the glare. It is like trying to see a small flame beside a floodlight. To overcome this, Astronomers use a method called coronagraphy. A coronagraph is a device that blocks the light of a star using a small disk, allowing surrounding regions to be observed more clearly. By reducing the star's brightness, it becomes possible to search for nearby objects. But even this method struggles here. The proximity and intensity of Alpha Centauri's stars makes suppression difficult. The light spreads, diffracts, and overwhelms sensitive detectors. Precision must be extreme, and even then, certainty remains elusive. In the year 2021, a team using the Very Large Telescope reported a possible signal near Alpha Centauri A. Using mid-infrared coronagraphy, they detected a faint source, tentatively labeled Candidate C. The signal was intriguing, but its nature remains uncertain. It could represent a planet, or it could be dust, or a background object aligned by chance. Without further confirmation, it remains unresolved. Webb approaches the problem differently. Its sensitivity to infrared radiation makes it capable of detecting heat signatures, not just reflected light. A warm planet emits energy that can be distinguished under the right conditions. This opens a path that does not rely solely on visible contrast. Alpha Centauri remains a priority, but one target stands out above the rest. Proxima b offers a possibility that extends beyond detection. It offers the chance to study an atmosphere, if one exists. This depends on alignment. If the planet passes directly between its star and our line of sight, an event called a transit occurs. During a transit, a small portion of starlight passes through the planet's atmosphere before reaching us. That light carries information. This is spectroscopy. Spectroscopy means analyzing light by splitting it into its component wavelengths. Different gases absorb specific wavelengths, leaving patterns that reveal their presence. Oxygen, methane, water vapor, each leaves a distinct signature, but the geometry must be precise. Current estimates suggest only about a 1.5% chance that Proxima b transits its star from our perspective. Without that alignment, this method cannot be used. So we wait, not passively, but with instruments prepared, calculations refined, and attention focused. The telescope is capable. The question is whether the alignment allows us to use it. A thin layer of gas can change everything. It does not look like much from a distance, just a faint envelope around a world. But it controls temperature, chemistry, and the possibility of stability. Without it, a planet is exposed. With it, complexity becomes possible. So the question turns to composition. If we could detect an atmosphere on Proxima b, the discovery would reach far beyond a single planet. It would show that Earth-sized worlds in harsh environments can hold onto their gases over long periods. That alone would reshape expectations. But the details matter more than the presence. Different gases tell different stories. Nitrogen, for example, is relatively stable. It does not react easily, and it forms the bulk of Earth's atmosphere. Carbon dioxide, on the other hand, plays a role in temperature regulation, trapping heat through a process called the greenhouse effect, where certain gases absorb and re-emit infrared radiation. If we found mostly nitrogen and carbon dioxide, it would suggest a planet with geological activity, perhaps volcanic processes releasing gases over time. It might be stable, but not necessarily alive. Add oxygen, and the picture shifts. Oxygen is highly reactive. It binds quickly with other elements, forming compounds and disappearing from the atmosphere unless something continually replaces it. On Earth, That replacement comes from photosynthesis, the process by which plants and microorganisms convert light into chemical energy, releasing oxygen as a byproduct. Without such a process, oxygen would fade. So its presence, especially in large amounts, would raise questions that cannot be easily dismissed. It would suggest ongoing production. But the most compelling signal involves a combination. Methane and oxygen together create a chemical tension. Methane is a simple carbon-based gas, and it reacts readily with oxygen. When both are present, they tend to destroy each other over time. Their coexistence implies continuous replenishment. This pairing is known as a biosignature. A biosignature is a pattern in the atmosphere that is difficult to explain without biological activity. It is not proof, but it is a strong indication that processes beyond simple chemistry may be at work. So far, no such signature has been confirmed beyond our solar system. But even without that combination, other signals carry meaning. Water vapor would indicate the presence of one of the key ingredients for life as we understand it. It would suggest that liquid water might exist somewhere on the planet, under the right conditions. Carbon dioxide, in large amounts, could point in another direction. Too much of it can drive a runaway greenhouse effect, where heat becomes trapped so effectively that surface temperatures rise uncontrollably. This is believed to have happened on Venus, transforming it into a hostile environment. Each outcome tells a different story, not just about the present, but about the planet's past, how it formed, how it evolved, and what forces shaped it. The atmosphere becomes a record, written in gases, waiting to be read. But reading it depends on alignment, sensitivity, and time. If conditions allow, instruments already in place may begin to extract that story, one wavelength at a time. A simple question can linger longer than any answer. In the year 1950, during a casual lunch, Enrico Fermi asked something that continues to echo through modern science. Where is everybody? The question sounds informal, but it points to a contradiction. The universe contains hundreds of billions of stars, many with planets. The conditions that led to life here may not be unique. If that is true, then intelligent civilizations should exist elsewhere. Yet we see nothing. This tension is known as the Fermi Paradox. It describes the gap between the high probability of life arising somewhere and the absence of clear evidence that it has. No confirmed signals, no artifacts, no visitors. Alpha Centauri sharpens this problem. It is close, not in human terms, but in cosmic ones. If a technological civilization had emerged there, even with a modest head start, it would have had billions of years to develop capabilities far beyond ours. Over such timescales, interstellar travel, even if slow, becomes feasible. They would have had time to explore, time to reach neighboring systems, time to leave traces that might still be detectable. Yet when we observe this system, we find no clear indication of such activity. That absence becomes part of the data, but interpretation remains uncertain. One possibility is that intelligent life is extremely rare, and Alpha Centauri never developed it. Another is that civilizations tend to end before they reach interstellar capability, limited by internal factors we do not yet understand. There is also the possibility that travel between stars is far more difficult than current models suggest. Even advanced civilizations may face limits that prevent expansion beyond their home systems. Or perhaps the signals they produce are not easily detectable, either because they are weak, short-lived, or transmitted in ways we do not yet recognize. We may also be looking incorrectly. Detection methods rely on assumptions about technology and behavior. If those assumptions are incomplete, we may overlook evidence that does not match expectations. Search efforts continue. The SETI Institute has directed attention toward Alpha Centauri, scanning for narrow-band radio signals that might indicate artificial origin. These searches focus on frequencies unlikely to be produced by natural processes. One such effort involved the Meerkat Telescope Array in South Africa. In the year 2020, a signal labeled BLC-1 was detected from the direction of Proxima Centauri. It appeared at a frequency of 982.002 MHz. It was narrow, stable, and initially passed several filters designed to remove human-made interference. For a time, it held attention, but further analysis revealed a different source. The signal was traced to interference from human technology, not an extraterrestrial origin. The pattern that seemed unusual had an explanation closer to home. Still, the process mattered. The fact that the signal passed initial screening and required months of careful study reflects the level of scrutiny applied to this region. Alpha Centauri remains a focal point, not because it offers answers, but because it sits at the intersection of possibility and silence. Most stars in the galaxy live quiet, dim lives. They do not dominate the sky, and they rarely draw attention, yet they make up the majority. Proxima Centauri belongs to this group, a class known as red dwarfs, or M-type stars. These stars are everywhere. Astronomers estimate that roughly 70% of all stars in the Milky Way fall into this category. They are small, cool, and faint compared to stars like our Sunday. Even when they are relatively close, they remain invisible to the unaided eye. Proxima is one of them. Its total luminosity, meaning the energy it emits, is only about 0.0017 times that of the Sunday. In simpler terms, it produces roughly 1/600th as much light. If placed where the sun is, it would barely illuminate the sky. Its surface temperature reflects this difference. At around 3042 Kelvin, it is much cooler than the sun, which sits near 5778 Kelvin. Temperature determines color in stars. Cooler stars glow red. Hotter ones shift toward white and blue. Proxima radiates a deep red light. Dim, but persistent. What it lacks in brightness, it makes up for in longevity. Stars generate energy by fusing hydrogen into helium in their cores. Larger stars burn through this fuel quickly. Smaller stars consume it slowly. Proxima is extremely efficient. It is expected to continue fusing hydrogen for about 4 trillion years. That is not a simple extension of time. It is hundreds of times longer than the current age of the universe. While our sun will exhaust its fuel in about 5 billion years, Proxima will continue almost unchanged. This changes the scale of possibility. Any planet orbiting such a star would receive a stable energy source not for billions, but for trillions of years. If conditions allow, processes could unfold over spans of time far beyond anything experienced on Earth. But Proxima behaves differently on the inside. Unlike the Sun, which has distinct layers, Proxima is fully convective. Convection means that material moves continuously within the star, rising and falling as heat is transferred. In the Sun, this motion occurs only in the outer layers. In Proxima, it occurs throughout the entire structure. Everything circulates. This constant movement allows magnetic energy to build and release across the whole star. It does not remain confined. When it releases, it produces flares, sudden bursts of radiation that vary in intensity and frequency. This is why Proxima is active. Its internal structure supports unpredictable magnetic behavior, leading to repeated energetic events. The same process that extends its life also drives its variability. From Earth, however, none of this is visible directly. Despite being the closest star beyond our Sun, Proxima appears as a point of light too small to resolve into a disk. Its angular diameter, the apparent size it occupies in the sky, is about 1,000th that of the Sunday. Even powerful telescopes cannot reveal its surface. So we infer its nature through light, through measurement, through patterns that repeat and confirm. A star that is faint, long-lived, and internally dynamic, shaping its surroundings in ways that are subtle but persistent. Before measurement, before distance had meaning, people looked up and gave the sky structure through memory. Patterns formed, not from calculation, but from repetition, from watching the same lights return night after night. Among those lights, one stood out in the southern sky. Alpha Centauri was already known. To those who lived in regions where it was visible, it became part of orientation, part of story, part of identity. It was not a system of stars. It was a presence, fixed and reliable, used to understand direction and time. In ancient Egypt, this star was associated with a figure called Khenti Iabet, a deity linked to the eastern horizon. The connection reflects how stars were integrated into belief systems, where celestial motion mirrored cycles of life, death, and renewal. Further south, knowledge took different forms. The Burong people of northwestern Victoria incorporated Alpha Centauri and its nearby companion into a detailed oral tradition. They identified the pair as Bermbermgel, two brothers known for their skill in hunting. These stories were not separate from observation. They encoded it. The position and movement of stars became part of a system that guided travel, seasonal change, and social knowledge. The sky functioned as both narrative and map. Across the ocean, another interpretation emerged. In ancient Chinese astronomy, Alpha Centauri was included in an asterism known as Nan Main, meaning Southern Gate. An asterism is a recognizable pattern of stars, often forming part of a larger constellation system. This pair marked an entrance, a symbolic boundary in the sky, a threshold. In the Andes, the Inca developed a different structure. Their Sikh system, a network of sacred lines extending from the Temple of the Sun in Cusco, connected physical landmarks with celestial reference points. Bright stars in the southern sky, including Alpha Centauri, were integrated into this system. Astronomy was not separate from governance. It influenced ritual, agriculture, and political authority. Knowledge of the sky carried weight, not just for navigation, but for maintaining order within society. As observation became more formalized, interpretation shifted. With the development of telescopes and modern astronomy, Alpha Centauri moved from myth into measurement. It became an object of study, its properties defined by data rather than narrative. But the sense of significance remained. In the modern era, it entered imagination again. Writers and creators began to treat it as a destination. Isaac Asimov referenced nearby stars in his work, framing them as reachable in distant futures. The video game Sid Meier's Alpha Centauri placed human civilization there, exploring themes of colonization and identity. In the film Avatar, a fictional moon in the system became a setting for human expansion. The idea persisted. When Proxima b was announced in 2016, the response extended beyond scientific circles. The discovery felt immediate, as if a nearby address had been identified. The distance remained vast, but the concept became more concrete. Astronomer Carl Sagan described nearby stars as potential future homes, not as speculation, but as part of a long trajectory of exploration. So the star remained consistent, observed, interpreted, reinterpreted, a fixed point in the sky, carrying different meanings across time, yet always present, waiting to be understood in whatever way each era could manage. Your body carries assumptions about where it belongs. Every system inside you expects gravity pulling downward, air pressing gently from all sides, and a steady rhythm of light and darkness. Remove those conditions, and the body begins to change. In microgravity, the absence of weight alters circulation. Blood and other fluids shift upward toward the head, since there is no force drawing them down. The face appears swollen, sinuses feel congested, and pressure builds behind the eyes. Over time, this can affect vision, reshaping the eye itself. The heart adjusts as well. Without gravity, it no longer works as hard to move blood upward. It becomes slightly weaker, adapting to reduced demand. This adaptation is efficient in space, but problematic when returning to a gravitational environment. Bones respond even more dramatically. Bone tissue is constantly rebuilt through a balance of formation and breakdown. On Earth, weight-bearing activity maintains that balance. In microgravity, that stimulus disappears. Bone density decreases at a rate of about 1 to 2% per month. Over time, structure fades. Without intervention, bones become fragile, increasing the risk of fracture. Muscle follows a similar pattern. Without resistance, muscle fibers shrink, losing strength and endurance. Even simple movements become harder over extended periods. Astronauts on the International Space Station exercise for about 2 hours each day. This slows the process, but does not stop it entirely. But physical degradation is only part of the challenge. Space introduces radiation at levels not experienced on Earth. Cosmic rays, high-energy particles from distant astrophysical events, pass through spacecraft walls and interact with biological tissue. They damage DNA. This increases the risk of cancer and may affect cognitive function over long exposures. Shielding can reduce this risk, but it adds mass, which complicates propulsion. So, alternatives are considered. One approach is artificial gravity. This can be created by rotating part of the spacecraft. As the structure spins, centrifugal force, which is the outward push felt in a rotating system, simulates the effect of gravity. The design must be precise. If the rotation is too fast, it causes disorientation and nausea. This is due to the Coriolis effect, where moving within a rotating frame creates unexpected forces. A larger radius allows slower rotation, reducing these effects and creating a more stable environment. But the body is not only physical. Psychological conditions change as well. Isolation grows as distance increases. Communication delays expand from minutes to years, removing real-time interaction with Earth. Conversations become asynchronous, responses arriving long after questions are sent. The connection fades. Studies from Antarctic stations and submarine crews offer partial insight. Extended confinement leads to sleep disruption, reduced activity, and increased tension among individuals. These effects appear even over months. Extend that to years or decades. The environment remains constant, the external view unchanging, the social group limited. Maintaining mental health becomes as critical as maintaining physical function. Systems must support not just survival, but stability of thought and behavior. So the challenge is layered. It is not enough to build a ship that moves. It must also sustain the complex, interdependent systems of the human body and mind continuously, without interruption, across a journey that stretches beyond any experience we have yet endured. Instead of stretching life across the journey, you imagine compressing it. Time would still pass outside, measured in years and centuries, but inside the body something quieter would happen. Processes would slow, signals would fade. The long duration between departure and arrival would be crossed not by endurance, but by absence. This idea rests on a real biological state. Torpor is a condition seen in many mammals where metabolism, the set of chemical reactions that sustain life, is dramatically reduced. In hibernating bears, metabolic rate drops by roughly 75%. Heart rate slows, body temperature falls, and activity nearly stops. Yet life continues. The animal survives for months without food or water, sustained by stored energy and tightly regulated physiology. Waste production is minimized. Tissue damage is avoided through mechanisms still being studied. Humans do not naturally enter torpor, but medicine has found ways to approach it. Therapeutic hypothermia lowers body temperature intentionally, slowing cellular activity during critical moments. After cardiac arrest, this technique can protect the brain by reducing its demand for oxygen. It buys time. Cells consume less energy, damage spreads more slowly. The body, temporarily quieted, becomes easier to preserve. But this state is limited. It lasts hours or days, not months. Extending it further introduces risk. Prolonged cooling can disrupt normal function, leading to complications in circulation, immune response, and cellular repair. The challenge is not only entering a reduced state, but maintaining it safely over long durations. But research continues. In 2014, a study supported by NASA explored the possibility of induced torpor for space missions. The proposal suggested cycling crew members through periods of reduced metabolism lasting several weeks. Others would remain awake. This rotation would reduce food and water requirements, since fewer active bodies consume fewer resources. It would also limit psychological strain, distributing the burden of wakefulness across the crew. The ship becomes quieter. Energy use drops. Movement slows. Time feels less continuous, more segmented. But this is not true suspended animation. The body remains active, only reduced. True suspension is more extreme. It would require halting biological processes almost entirely, then restarting them without damage. The primary obstacle is ice formation. When cells freeze, water expands into crystals that rupture membranes and disrupt internal structures. This damage is irreversible. Cryopreservation, the preservation of biological material at very low temperatures, works reliably for embryos and small samples. But scaling this to a full human body introduces complexity that has not been solved. Rewarming is the problem. Temperature must be restored evenly and precisely. Any imbalance can cause further damage. So far, no method has demonstrated safe revival of a fully preserved human. So the dream remains partial. A torpor-based system appears more plausible in the near term. It does not eliminate time, but it reshapes how time is experienced. Long stretches of the journey would pass without awareness, broken into intervals of wakefulness. You would not sleep through centuries, but you might pass through them differently. You arrive without stopping. There is no gentle insertion into orbit, no gradual survey of the system. A probe moving at 1/5 the speed of light crosses interstellar space for decades, then encounters its destination in a single, irreversible sweep. Everything must happen quickly. At that velocity, Alpha Centauri is not a place you enter, but a region you pass through. Hours define the encounter. Every instrument must already be active, calibrated, and waiting. The mission becomes choreography. Cameras begin capturing images long before closest approach, building resolution as distance shrinks. Spectrometers analyze incoming light, splitting it into wavelengths to reveal chemical signatures in atmospheres and dust. Each second matters. Magnetometers measure magnetic fields, detecting how stellar winds shape the surrounding space. Particle detectors register charged particles, tracing interactions between stars and any planetary environments. Data accumulates rapidly, but storage is limited. Transmission is harder. The probe must compress its findings into a stream small enough to send across 4.37 light-years, using a transmitter no more powerful than a handheld device. Then it sends everything home. Signals travel at light speed, the fastest possible rate. Even so, they take over 4 years to return. From launch to first data receipt, nearly a quarter-century passes. You wait. If the geometry aligns, one target becomes central. Proxima b, passing through the probe's field of view, could be imaged directly, not as a detailed landscape, but as a resolved disk or shifting point, carrying subtle variations in brightness. Enough to hint. Atmospheric analysis would rely on spectroscopy, the study of how matter absorbs and emits light. If starlight passes through a planetary atmosphere during alignment, specific wavelengths are absorbed, leaving identifiable patterns. Each pattern is a clue. Water vapor, carbon dioxide, methane, oxygen, each leaves a distinct imprint. Detection does not confirm life, but it defines the environment. It tells you what is possible there. But the probe cannot stay. There is no braking system. No fuel reserve exists at this scale. The spacecraft continues outward, leaving the system behind almost as soon as it enters. The encounter is brief. This mirrors earlier explorations. When Voyager 1 passed Jupiter and Saturn, it revealed entire worlds in days. It transformed understanding, yet left questions unanswered. This would be similar. We would gain the first direct look at a nearby star system, measure its structure, and test decades of theory. But we would not land, not sample soil, not confirm life. Presence remains distant. To go further, multiple probes might be launched over time, each refining the picture. Or new methods could emerge, allowing deceleration through interaction with stellar winds and magnetic fields, a concept known as magnetic sailing. It remains unproven, so the first arrival is not an ending, it is a moment of contact, brief and incomplete, where a distant system becomes real for the first time, and then it is gone again. Arrival does not mean survival. Reaching another star system, even after decades or centuries, would only complete the first part of a much larger problem. The moment you step beyond the spacecraft, the question becomes immediate and unforgiving. Can you live here? Nothing guarantees the answer is yes. Unlike earlier migrations across Earth, where air, water, and gravity were already familiar, this environment offers no such assurances. Every assumption must be tested, every condition measured. Breath comes first. A breathable atmosphere requires a precise balance, roughly 21% oxygen, 78% nitrogen, with trace gases in narrow ranges. Too little oxygen, and cells starve. Too much, and combustion becomes dangerously easy. This balance is rare. Even if an atmosphere exists, it may be dominated by carbon dioxide, methane, or other gases incompatible with human biology. In that case, survival depends entirely on controlled environments. So habitats define life. These would be sealed structures, pressurized and regulated, maintaining stable air composition, temperature, and humidity. Inside, ecosystems must be recreated, plants cycling carbon dioxide into oxygen, water continually filtered and reused. Nothing is wasted. Food production becomes a closed-loop system. Hydroponics, growing plants in nutrient solutions without soil, allows efficient use of space and resources. Every gram of matter must circulate through the system repeatedly. Energy sustains everything. Power generation must be constant and reliable, whether from nuclear reactors, solar arrays adapted to local light conditions, or other advanced systems. A failure in energy cascades quickly into failures in life support. There is no margin. But even with functioning systems, time stretches differently. Communication with Earth takes over 4 years each way. Guidance becomes delayed beyond usefulness. Decisions are local. Medicine must operate independently, with full capability to diagnose and treat without external consultation. Manufacturing must produce replacement parts, tools, and materials from available resources. Industry becomes internal. Terraforming, the process of altering a planet's environment to resemble Earth, remains speculative. It would involve changing atmospheric composition, temperature, and possibly magnetic protection over immense timescales. Thousands of years at least. So, early generations would live entirely within constructed environments, never experiencing open air. Their world would be bounded by walls, however expansive those spaces become. But the deeper challenge is not mechanical. It is human. A colony would exist with no possibility of return. The distance is too great, the energy required too immense. Earth becomes a place of origin, not a destination. Memory replaces connection. Culture, language, and identity begin to shift. Over generations, the idea of Earth may become abstract, preserved in records and stories rather than experience. You would belong to a new world, and yet that world would still depend on fragile systems maintained continuously without interruption. Survival would not be a moment of arrival, but a condition sustained every day, forever, or until it fails. Step outward just a little further, and the isolation begins to soften. Alpha Centauri feels singular because it is closest, because it anchors our sense of direction beyond the solar system. But distance in space is layered, and once you expand your view to 15 light years, a pattern begins to emerge. We are not alone here. Within that radius lie roughly 56 star systems, containing around 70 individual stars. Each one occupies its own gravitational domain, each one separated by distances that feel immense, yet repeat with quiet regularity. Another neighbor waits just beyond. Barnard's star sits at about 5.96 light-years, a faint red dwarf moving steadily toward us. Its motion across the sky is faster than any other known star, a slow drift measured over decades. It will come closer. In roughly 10,000 years, it will overtake Proxima Centauri as the nearest individual star. This motion is not dramatic, but persistent, revealing that even stellar neighborhoods are not fixed. But proximity does not guarantee discovery. A potential planet, Barnard's star B, was announced in 2018, described as a super-Earth. Further analysis raised doubts, suggesting the signal may have come from stellar activity rather than an orbiting world. Uncertainty remains. Farther out, at 8.6 light-years, Sirius dominates the night sky. It appears brilliant from Earth, but its brightness comes from intrinsic power, not closeness alone. It is a binary system, a white dwarf, a dense stellar remnant, orbits alongside a larger main sequence star. This pairing reflects a later stage of stellar evolution, where one star has already exhausted its fuel and collapsed into a compact form. Time leaves marks here. At 11.9 light-years, Tau Ceti offers a different picture. It resembles our Sun more closely, both in size and stability. Observations suggest multiple planets may orbit it, with at least one candidate lying within the habitable zone. Possibility expands. When astronomers examine nearby systems with sufficient precision, planets appear frequently. Detection methods improve, revealing subtle gravitational effects and faint signals embedded in starlight. Patterns become clear. Rocky planets, similar in size to Earth, seem to form around many stars. Gas giants appear as well, but smaller worlds are not rare exceptions. They are part of a broader structure repeated across systems. But conditions vary. The presence of a planet does not guarantee habitability. Temperature, radiation, atmospheric composition, and orbital stability all shape whether a surface can support liquid water. Complexity defines the outcome. Alpha Centauri remains significant because it is closest, because it offers the shortest path to another system. Yet it is only one example within a wider distribution of nearby stars. The neighborhood is populated, not densely, not in any human sense, but consistently enough that patterns emerge. Stars are separated by several light-years, yet arranged in a loose network, each with its own potential for planets and environments. You begin to see structure. The nearest star is not an isolated destination. It is the first step into a region where systems repeat, where the question of life extends beyond a single point, and where distance, though vast, is no longer singular. Turn the perspective around, and you begin to disappear. From within the Alpha Centauri system, looking outward instead of inward, our solar system becomes just another distant point among many. The Sun is still visible, still present, but stripped of its central importance. It blends into the sky. Its brightness would register at about magnitude 0.5, placing it among the more noticeable stars, yet not dominant. Many stars would outshine it, depending on location and conditions. It is visible, but not special. Placed against the background of that sky, it would sit within the constellation Cassiopeia, forming part of the familiar pattern we recognize as a tilted W. From that vantage, the shape remains, though slightly altered by perspective. Constellations shift subtly. The change is small across a distance of just over 4 light-years, yet enough to remind you that these patterns are not fixed structures. They are alignments seen from a particular place. Move the observer, and the pattern bends. But the Sun itself offers little detail. To the unaided eye, it appears as a steady point of light. Through telescopes, it would still be difficult to isolate. Planets vanish first. Earth, orbiting at 1 astronomical unit, becomes invisible almost immediately at that distance. An astronomical unit, the average distance between Earth and the Sun, is far too small a separation to resolve across interstellar space. The planet is lost in glare. Even the most advanced telescopes currently conceived would struggle to image Earth directly from Alpha Centauri. The brightness of the Sun overwhelms the faint reflected light of any orbiting body. Detection becomes indirect. Only through subtle shifts, gravitational effects, or minute variations in starlight could a distant observer infer that planets exist at all. Even then, identifying one as habitable would require sustained observation and precise measurement. There is no obvious signal. A civilization there, studying its sky, would see our Sun as one star among thousands. It would not stand out as a place of significance, nor suggest the presence of a world filled with life. We are hidden in plain sight, but this invisibility is mutual. The same limitations that obscure Earth from Alpha Centauri also obscure any small worlds there from us. Distance and brightness create a barrier that light alone cannot easily overcome. Silence adds to the effect. Humanity has transmitted radio signals for just over a century. These signals expand outward at light speed, forming a sphere roughly 120 light years in radius. It sounds large, but signal strength fades with distance. By the time these transmissions reach Alpha Centauri, they are already extremely weak, blending into background noise unless detected with highly sensitive equipment. Most signals disperse unnoticed. Even deliberate messages, such as powerful directed broadcasts, diminish rapidly. Detecting them requires not only proximity, but also alignment, timing, and intent. So, across this short distance, we remain effectively quiet. You could observe the sky for years and never suspect a modest star, a faint signal, a distant system with no obvious signature of life. From there, we are not a destination. We are a possibility, hidden within the light. Long before systems fail, the mind begins to shift. You can carry enough food, recycle air, shield against radiation, but cognition and emotion follow patterns shaped on Earth. Remove those patterns, stretch time beyond familiar scales, and subtle changes begin to accumulate. They do not arrive suddenly. Research into isolation offers a glimpse. In Antarctic winter stations, small groups remain cut off for months, surrounded by darkness and extreme conditions. Communication is delayed, environments are unchanging, and social circles are fixed. Behavior adapts. Sleep cycles drift without consistent light cues, leading to irregular patterns and reduced rest quality. Motivation declines gradually, replaced by long periods of inactivity. This has been measured. The Mars 500 experiment, conducted between 2010 and 2011, confined 6 individuals for 520 days inside a simulated spacecraft. It remains the longest controlled isolation study of its kind. The results were quiet but consistent. Participants showed increasing sedentary behavior, reduced engagement, and disrupted sleep rhythms. 2 developed stress levels considered clinically significant. 1 withdrew further. Researchers described a pattern resembling torpor, a state of reduced activity and interaction. The subject became less responsive, conserving energy in a psychological sense rather than a physical one. But that study lasted less than 2 years. An interstellar mission extends far beyond that scale. Decades, even centuries, introduce conditions with no direct comparison in human experience. Time becomes diffuse. Without external milestones, without seasons or changing landscapes, perception of time can flatten. Days blend into one another. Weeks lose distinction. Memory shifts. What remains constant is confinement. Physical space does not expand. Social groups remain limited, with the same individuals interacting repeatedly across years. Tension becomes structural. Conflict, even minor, can persist longer without separation. Resolution requires continuous management, not avoidance. The system depends on stable relationships maintained deliberately, but the deeper effect may be more abstract. Earth becomes unreachable. Communication delays extend to years, removing the possibility of real-time exchange. Messages become archival rather than conversational, sent into the future without immediate response. Connection fades. A concept, sometimes called Earth sickness, begins to form, a persistent awareness that the place of origin cannot be returned to. Unlike homesickness, it has no resolution. There is no return path. Historical analogs offer partial insight. In the 18th century, transported convicts sent to distant colonies experienced a similar severance. Their homeland became an idea, preserved in memory but no longer accessible. Distance became permanent. But interstellar travel intensifies this further. Generations may pass aboard the vessel. Children are born who have never seen Earth, who understand it only through stories and records. Identity evolves. The original purpose of the mission, clear to those who began it, may lose immediacy over time. For later generations, the destination is abstract, something distant and inherited. Meaning must be sustained. Some thinkers suggest that survival requires a shift in perspective. The crew cannot remain travelers in a temporary state. They must become a stable society, where the ship itself is home. The journey becomes the world, and the destination, no matter how real, becomes something else. Hold the light in your mind for a moment. It left its origin years ago, crossing the dark without pause, carrying with it a snapshot of another place. When it reaches you, it feels immediate, present, part of now. But it is not now. It is delayed. The light arriving tonight departed in early 2021. While it began its journey, events unfolded here. Vaccines were distributed, observatories prepared for launch, lives shifted in ways that felt urgent and close. All of that is absent there. What you see is not the system as it exists, but as it was. The present of one place is the past of another. This separation, measured in years even between nearest neighbors, creates a quiet dislocation. Moments are not shared, but they coexist. Across this small interstellar gap, two histories unfold simultaneously, unaware of each other. You can imagine standing there, looking back, seeing Earth not as it is now, but as it was years ago. Perspective stretches. Alpha Centauri has persisted through all of it for roughly 4.85 billion years. It has burned steadily through the formation of our planet, through the slow emergence of life, through every human story ever recorded. It does not register any of it. Stars are indifferent. They fuse hydrogen into helium, releasing energy that travels outward in every direction, unconcerned with what may or may not exist around them. Their timelines extend far beyond ours. But proximity changes meaning. In a universe where the nearest galaxy lies 2.5 million light-years away, and the observable edge extends tens of billions of light-years in all directions, a separation of just over 4 light-years becomes small, almost intimate. By cosmic standards, these two systems occupy the same neighborhood. They share a region of the Milky Way, embedded within the same spiral arm, shaped by similar conditions long ago. Their origins are related. Both formed from the collapse of molecular clouds, vast regions of gas and dust enriched by earlier generations of stars. Elements heavier than hydrogen and helium, carbon, oxygen, iron were forged in ancient stellar interiors and scattered outward. That material became everything: planets, oceans, atmospheres, and the molecules that make up living organisms, all trace back to those earlier processes. In that sense, the matter composing your body and the matter composing distant worlds share a common ancestry. You are connected at the level of atoms. This idea aligns with a broader concept, sometimes called the mesh, a term used to describe the interconnectedness of systems across scales. In a cosmological context, it suggests that no object is entirely isolated. Everything participates. Gravity links stars across vast distances. Chemical processes repeat in different regions. Structures emerge from shared physical laws, but connection does not erase distance. Alpha Centauri remains far beyond immediate reach, separated by space that cannot be crossed easily. It is both near and unreachable, familiar and distant at once. You exist within the same structure, and yet between you and that light, there is still the long, silent stretch where time separates everything. Before any engine ignites, the movement has already begun. It starts in the mind, in the quiet recognition that a point of light is not just light, but a place. You hold that idea, and it shifts something subtle, a sense that distance is not a boundary, but an invitation. The destination becomes secondary. Across history, journeys have followed this pattern. The tools are incomplete, the risks are poorly understood, and the reasons offered are never entirely sufficient. Practical needs are named: resources, safety, knowledge, but something else moves underneath. Early navigators crossed open oceans without maps in the modern sense. They read the sky, traced patterns in waves, watched birds and winds, building a system of knowledge carried in memory and tradition. It was enough. They reached islands beyond sight of land, places no one they knew had ever seen. Those places became home, not because they were certain, but because they were found. The act defined the outcome. But Alpha Centauri presents the same structure at a different scale. The distance is greater, the tools more complex, the uncertainty deeper, yet the underlying question remains unchanged. Do we stop or continue? So far, the answer has been consistent. Movement continues, even when the path is unclear, even when the cost is high. Progress is not always smooth, not always justified by immediate benefit, but it persists. There are reasons that can be measured. Scientific goals provide structure. Reaching another star system allows direct observation of planets, atmospheres, and environments beyond our own. Knowledge expands. Testing physics at high velocities offers insight into fundamental laws. Systems operating near fractions of light speed reveal behaviors that cannot be studied within the confines of our solar system. Limits are explored. Long-term survival also enters the discussion. The sun will exhaust its hydrogen fuel in about 5 billion years, altering conditions on Earth beyond habitability. Time extends beyond us. But these reasons, while valid, do not fully explain the drive. They describe outcomes, not origins. The impulse itself is simpler and older. You recognize it easily. A child looks upward and asks what a star is. The question is not driven by necessity. It emerges from curiosity, from the desire to understand what lies beyond immediate reach. It persists across time. Cultures separated by distance and history share this pattern. They look outward, interpret what they see, and imagine movement toward it. The scale changes, but the structure remains. But not every horizon is crossed. Some remain distant for long periods, waiting for conditions to align, for knowledge to accumulate, for tools to evolve. The desire does not disappear. It waits. It gathers. Alpha Centauri is one of those horizons. It is close enough to define a direction, yet far enough to resist immediate access. It holds both clarity and difficulty in balance. You can see it, but not reach it. So the question becomes less about arrival and more about orientation. What kind of species are we when faced with a boundary that can be perceived, but not easily crossed? The answer is still forming. And in that space between knowing and reaching, the movement continues quietly, long before any journey begins. You do not need a telescope to begin. You only need a clear horizon, a darkened sky, and a quiet moment long enough for your eyes to adjust. Somewhere beyond the familiar patterns, low in the southern sky or hidden just beneath it, that steady light continues its journey. It does not flicker with intention. It simply arrives, as it always has, crossing the final thin layer of atmosphere after traveling for over 4 years through near-perfect vacuum. That light began its path in the early months of 2021, leaving a distant system while events unfolded here, unnoticed by the source itself. The journey completes silently. Photons, the smallest packets of light, carry that energy across 41 trillion kilometers, uninterrupted, unaffected by time as we feel it. When they reach you, they transfer that energy into your eyes, into electrical signals, into awareness. It becomes something else. A distant fusion reaction. Hydrogen atoms combining under immense pressure transforms into perception inside a human mind. That chain of events stretches across space and ends in a moment you can barely hold. It happens constantly, but most of the time it passes without notice. The sky is too bright, the schedule too full, the attention elsewhere. The nearest star system continues its presence regardless, patient in a way that only astronomical time allows. Nothing about it changes for you, but everything about your understanding changes with each layer uncovered. The system remains what it is, a set of stars bound by gravity, following paths laid out billions of years ago. You are the one moving forward. There is still much we do not know. The surfaces of its planets, if they exist in stable orbits around the brighter pair, remain unresolved. The conditions on the small world around the red star are still inferred, modeled, debated. Uncertainty remains. But the boundary between imagination and measurement has shifted. Instruments refine distances to fractions of a percent, detect motions smaller than a walking pace, and search for atmospheres across interstellar space. Precision grows quietly. But even as knowledge expands, the star itself does not respond. It does not signal back, does not change brightness in recognition, does not acknowledge the attention directed toward it. It simply continues burning. You are left with a strange duality. The system is both close and unreachable, a neighbor by cosmic standards, yet beyond any immediate physical journey. It sits at the edge of what can be touched and what can only be observed. Both are true. In that balance, something subtle forms. The distance is not just a barrier, it is a measure of scale, a reminder of where you stand within a much larger structure. Perspective settles in, and still, each night it remains, unchanged in its presence, unchanged in its distance, offering the same steady signal across time. It does not move closer for you, does not grow brighter with effort. It waits without waiting. So when you look toward that part of the sky, whether you see it or not, you are aligned with something that has outlasted every moment of human history and will continue long after. The star is always there,